All right, you're welcome. Sorry for that interruption. I wanted to adjust the settings so that it can be recorded. I'm very sorry for that. So we'll continue from where we stopped. I noticed that it needed some more setting. Sorry for that. And thank you for reminding me about that. So as we were talking, let's take some of the questions related to this. Question number one is below change to 1A, solid B, critical pressure. The gas can be changed. Balance of the plot of pressure against volume. Resemblance of the plot of pressure against, that is why we have Boyle's law. So that's why we have Boyle's law. Are you still seeing the PowerPoint? Hello? Are you still seeing the PowerPoint? Hello?
Yes, sir.
Okay. All right. So the pressure corresponding to the temperature above which a gas cannot be liquefied is called what? That is critical pressure. That is the answer there. So now we will move to the next slide. We'll move to the next slide, which is derivation. The van der Waals equation can be written as PV. That's the equation can be written in form of the ideal gas equation. That is PV is equal to nRT. That's the basic ideal gas equation. So now what is P? The actual pressure occupied by the real gas is now P plus A all over V squared. That's if it can be P plus A n squared if it's more than one if it is more than one atom. That should be A n squared. Then multiplied by the volume V minus B for 1 mole of a gas. So it's equal to RT. That means product of pressure and volume. We see that the actual pressure occupied by 1 mole of a gas is P plus AB squared. And then this one should be P plus AN squared. Please, you take note of that correction. They have corrected before I send out the slide. So it's equal to nRT. So now you see pressure times volume. Yeah, for you to have pressure times volume, you will now begin to see what can you do to it. So if you now spread this equation, multiply out this equation, we have P is equal to plus AN all over V minus PB. If you are multiplying this out, this is what you have. You have equation 2. Now, if you look at it again, you'll find out that you can rearrange it for that PV minus PB plus A over V. That's for 1 mole of gas, all over AB, all over V squared is equal to RT. That's equation 3. So now if you multiply equation 3 by a formula, the molar volume of a gas, that's the square of the molar volume of a gas all over pressure, you have the next equation, which can be simplified to this. You don't really need to derive this equation, but it's good for you to know. So that means this is a value for the molar volume of a gas. So our major interest now is to know how to calculate the cubic equation will yield 3 values for Vm corresponding to. So this is what you call a cubic equation. All the 3 values of Vm, that's the molar volume may be real, or one may be real, and the other 2 may be complex, conjugate. So it is not something, what is most important for you is how do you calculate A, the value of the van der Waals constant, how do you calculate B, and how do you calculate the critical temperature. So that is the important thing. This is the most important aspect for you. The oral derivation is not within your scope. So if you want to know, you can still know. But most of the time, it's better to present an idea of a situation for you. So this is the most important aspect. You should know this formula. This is the van der Waals equation for 1 mole of gas. This is how to calculate the van der Waals constant. A is equal to 27 RT squared all of us. So that is the most important thing. You should know. Calculate the van der Waals constant A and B. Given that the critical volume is 22.4 dm cube and the critical temperature is 273 Kelvin. So you now look at what is A. We are written A. What is B? You can look at the formula. So you see 9 over 8. It's simple to use 9 over 8 times R, which is 8.314 times T, the temp times TC. That's the one we are using times TC. The temperature, what's the temperature here? 273. We didn't multiply. We have to multiply by 273. 273 Kelvin times 22.4 dm cube. That's the critical reason. So what you will check your answer. Let me calculate and see if it is correct. You can also calculate with me. Let's see how it is, what it is. You can calculate with me to see the answer. So we can talk about 9 we have, sorry, 9 times 8.314 times 273 times 22.4 is equal to this divided by 8. The answer is 57,196.99. So that is the value of that Faraday's constant. So you can also check this one. It's simply the molar volume divided by 3. That is the volume of the B, Faraday's constant B. So that is correct for that. So you can check for yourself and confirm that. Question: the critical temperature of a gas is 298 Kelvin and the molar critical volume is this. Calculate the van der Waals constant A. At what pressure would the gas have the critical constant? So now look at it. The important thing is, can you calculate the van der Waals constant A? From here, you can also calculate the B. Once you know the critical volume, molar critical volume, of course, you can calculate B. So this is a way of applying that equation. So you can see for yourself. So liquefaction, what's the significance of liquefaction? It's a process of making a gas or solid to become liquid. We can make a solid become liquid by melting, and a gas can be changed to liquid by condensation. Take note of that. You can change a gas to liquid by condensation. The critical phenomena and our knowledge of the critical constant are useful in liquefaction of gases. Liquefaction of air is important in the manufacture of nitrogen. Nitrogen, of course, the process of manufacturing nitrogen is liquefaction of air. And the oxygen, which are both important, are important industrial chemicals. The liquefied petroleum gas, mixture of propane and butane, is used as domestic fuel. So liquefaction is also useful in the domestic fuel industry. So we have liquid helium and nitrogen are important for making the materials superconducting. Liquefiable gases such as ammonia and dichloromethane. That's from when dichloromethane are used in refrigeration and air conditioning. Air conditioner, yeah, conditioning. So that is dichloromethane. Dichloromethane. So that is it. Many substances like water, ethyl alcohol, etc., have high critical temperature and hence exist as liquid even at room temperature. While water and ethyl alcohol exist as liquid at room temperature. Other like ammonia, sulfur, 4 oxide, etc. under ordinary condition have low critical temperature, but can be easily liquefied by cooling using freezing mixture under moderate pressure. Take note that many substances like water, ethyl alcohol, etc., have high critical temperature. That means it will take a very high temperature for them to be changed to gas. So freezing of the mixture lower the temperature of a substance. For instance, if you put water in a freezer, you will see that the temperature is lower below, and it will lower it below the critical temperature. So if the one way you can make a gas or a substance for its temperature to be lower or to be below the critical temperature, that's for to turn it to liquid is to lower the temperature. So like some gases, if you lower the temperature, they will change to liquid. Why do freezing lower the temperature? So you take note about that. The critical temperature is actually makes lower. Why do boiling increases the temperature? What is the usefulness of critical constant? So you can take note of that. The answers are written there. So liquefaction. On the other hand, there are many gases like oxygen, nitrogen, hydrogen, and helium whose critical temperature are much lower. That means you can easily turn them to liquid. Special methods are adopted to cool this gas below their critical temperature. Two common methods of cooling these gases are the Linde's method and the Claude's method. So take note of these two methods to make gases such as oxygen, nitrogen, and helium. You can use the Linde's method, you can use the Claude's method to cool them below the critical temperature. So the Linde's method is based on the principle of Joule-Thomson effects. So see that I've highlighted that for you to know what is the basis, the principle of the Linde's method. The expansion of a gas from a region of high pressure to a region of low pressure lowers temperature. So when you move from higher temperature to lower temperature, you lower or will move from high pressure to a region of low pressure. You will actually achieve a lower temperature. Charles' law, you remember Charles' law, the pressure is proportional to temperature. If you increase the pressure, you increase the temperature. So if you lower the pressure, that's it. But in other words, if you lower the pressure, you also lower the temperature. The gas does not do any external work, but the kinetic energy of the molecule expends some works to overcome the attractive force between the molecules. So the temperature of the gas is lower. To have a cooling effect, a gas is brought below a temperature called its inversion temperature before allowing it to expand. In the Linde's method, you see the temperature is lower and the gas is brought below its what you call inversion temperature. And then it is allowed to expand. That is the principle of the Linde. So the Joule-Thomson coefficient of a gas can expand or contract. If the expansion of a gas leads to cooling, such gas is said to have a positive value of Joule-Thomson coefficient. But if expansion leads to heating, the gas is characterized by a negative value of Joule-Thomson coefficient. So given the following Joule-Thomson coefficient, state the gas that will be most suitable for application in refrigeration. So the one that have which one? You say when the one that will be having positive value of Joule-Thomson coefficient will be good for refrigeration, because if it has positive value of Joule-Thomson coefficient, it means cooling expansion will lead to cooling. So that is the one that will be good for that. Question: in which of the following device do you expect the employment of a gas with positive value of a Joule-Thomson coefficient? I've mentioned refrigeration, I've mentioned air conditioning, and other similar purposes. Which of the following gas has positive value of the answer here, in which of the following do you expect the employment of a gas with negative value? Because for this one, you should have negative value. Which of the following gas has a positive value of Joule-Thomson coefficient? Freon. Freon, of course, is the answer because it's normally used in a refrigeration. So I can change this one to black to green so that you don't get worried. In which of the following device do you expect the employment of a gas with negative value of your Thomson coefficient? Room heater is an example. For the Linde's liquefaction method to work, the temperature of the gas must be brought to what? Must be brought below the what? Inversion temperature. So that's what we just taken the question. In the Linde's method of liquefaction, the gas do not exercise any form of external work, but what? Kinetic energy of the molecule. So the gas do not do any external work, but the kinetic energy of the molecule expends some work to overcome the attractive forces between the molecules. So that is what happens. So inversion temperature in thermodynamics and cryogenics is a critical temperature below which a gas that is expanding at constant enthalpy will experience a temperature decrease. That means until you reach the inversion temperature, it may not experience a temperature decrease, and above which will experience a temperature increase. Above the inversion temperature, it will be temperature increase, but below the inversion temperature, there will be temperature decrease. So take note of that. Substances with positive value of Joule-Thomson coefficient undergo cooling by expansion, but those with negative values of Joule-Thomson coefficient experience a rise in temperature. So that is what we see there. So question, for cooling to occur, the expanding gas must have the temperature below what? The inversion temperature. Just refreshing your memory. Below the inversion temperature, gas will experience what? So it will experience cooling, but above the inversion temperature, it will experience what? The temperature will rise. So the Claus method, which is still one of the other methods that can be used to liquefy gas like nitrogen, hydrogen, helium. So that has a very low Thomson coefficient. So another Claus method is more efficient than the Linde's method. There's a compressed gas in the insulated vessel under adiabatic condition is partly used to do work against a piston in a cylinder and partly expanded through a valve. The cool gas obtained by adiabatic expansion is used for cooling the incoming gas in the heat exchanger. The process is repeated till the gas is liquefied. So that is another. The Claus method of liquefaction, in the Claus method of liquefaction, the cool gas is obtained by what? That's adiabatic expansion. The cool gas in the Claus method of liquefaction is obtained by, of course, the same thing. So now let's look at, let's see what we can talk about intermolecular forces. Real gas deviate from the ideal gas behavior because of the presence of what? Intermolecular forces. The intermolecular forces are also responsible for the conversion of gas into liquid and solid. Remember, in one of the methods, we say that the gas molecule, the kinetic energy of the gas molecule must be expended to bring up cooling. So the intermolecular forces are very important in conversion of gases into liquid. They are also, because of they are important. It is very necessary to mention them here. So Van der Waal also developed a model that can explain the behavior of liquid. In recognition of his work, the weak intermolecular forces in liquid and solid are often called Van der Waal forces. What is the name for the weak intermolecular forces in liquid and solid? So Van der Waal forces there are three major components of the Van der Waal forces. One is the dipole-dipole interaction. The other one is dipole-induced dipole interaction. The other one is induced dipole interaction. That one is commonly called London or dispersion forces. What are the three components of the Van der Waal forces? We have seen that the dipole interaction, dipole-induced dipole interaction, and then the other one, induced dipole interaction. Dipole means that dipole actually exists between one and the other. But when it comes to dipole-induced dipole, that means one has a dipole, its own dipole, but the other one do not have. But it's now forced to have the dipole. That's why it's called dipole. The one it has, and the one that is forced to have dipole is induced dipole. So an induced dipole means that they are all the two interactions. The interaction exists by inducement. There's no permanent dipole for any of those molecules. So let's see that dipole-dipole interaction. So polar molecules, that's not compounds that are polar like water. if you look at it, the hydrogen will be partially positive charge, and the oxygen will be partially negative charge. So polar molecules can attract each other electronegatively. During this attraction, the positive end of the one molecule is close to the negative end of the adjacent molecule. Such an interaction is called dipole-dipole interaction. So you can see that in the liquid state, although molecules are in continuous motion, they tend to align themselves so that on the average, the intermolecular attractions are maximum. So the interaction energy between two polar molecules separated by a distance r is found to be directly proportional to the square of the product of the dipole moment of the two molecules and inversely proportional to temperature. So you can see that that is a very significant information. So you can see that intermolecular force is proportional to dipole moment. So intermolecular force will therefore be, it should be equal to the product of the dipole moment, then divided by the temperature. So and then multiplied by a constant. This is proportional to that. So electronegative interaction between partially charged positive and negative charge is called dipole moment. Dipole moment interaction is directly proportional to the square of the product of the dipole moment and inversely proportional to the temperature. Dipole interaction is maximized in liquid, and the molecule have aligned themselves. So once the molecule can align themselves more, it is actually maximized. So let me increase this font so that you can see better, have a better view. So that's that's the dipole-dipole interaction. Now, as we say, the dipole-induced dipole is one has its own dipole, partial charge, and the other one doesn't have. So you now force it to have. So not suitable for explanation of attractive force between polar molecule. The one that is suitable for explanation of attractive force between polar molecule at high temperature itself is the dipole-dipole. So a polar molecule can induce, now listen, a polar molecule now force the non-polar molecule to have dipole moment. So it can induce a dipole moment in a neighboring polarizable, it's a polarizable atom or molecule. An atom or molecule is said to be polarizable if its electron cloud can be distorted. Normally, electron cloud can be spherical, but if you can force it not to be spherical, it's said to be distorted. The ability of a species to undergo electronic distortion is described in terms of polarizability. So when a compound electron cloud can be distorted, we say it is polarizable molecule. So now, if you have a compound that has a dipole moment, so so you can induce it on the other one, and such is called dipole-induced dipole interaction. The electron charge cloud of a larger atom, one with a higher atomic number, can be easily distorted because the strength of the bonding between electron and nucleus decreases as the radius of the atom increases. That means if a molecule is very large, you can easily squish it, change its structure. But if it's very small, it may be very tough because the attraction is very high. So the strength of dipole inducement will now depend on the size of the molecule. Larger molecule can easily be polarized, that's distorted, and dipole-induced dipole interaction will set in. So now let's look at the dipole-induced dipole interaction. Large molecule of electrons, insignificant influence of the nucleus since it is far from the nucleus. The interaction energy between a dipole and an induced dipole separated by this and r is directly proportional to the square of the dipole moment of the polar molecule and directly proportional to the polarizability of the molecule. Polarizability is a distortion, that's to change the electronic cloud, and then it's inversely proportional to the 6th power of the distance of the separation. Take note of the other one. When we're talking about dipole moment, we're saying that it's proportional to what? The product of the dipole moment of the molecule of each of the constituting compound, and then divided by what? And it's inversely proportional to temperature. But this one is directly proportional to the square of the dipole moment, and it's also directly proportional to the polarizability of the molecule. It's also inversely proportional to the 6th power of the distance. When something is directly proportional, it means when you increase it one, the other one will increase. But when it's inversely proportional, when you increase one, the other one will decrease. So now the last one is a dipole-induced dipole dipole interactions. Now let's see this. A large molecule has a higher polarizability than a small molecule. For example, argon has higher polarizability than helium. Larger molecule, due to greater number, this should be dipole-induced interaction. We have treated others. So now you have a large molecule, you have small molecule, and he said that the larger molecule can easily be polarized. So larger molecule, due to greater number of electrons, have higher polarizability than smaller molecule. For example, ethane is more polarizable than methane. Propane is more polarizable than ethane, and so on. So the larger one will easily be polarized. The one that is higher, the one that have higher carbon compound. So dipole-induced dipole interaction between a polar molecule and a neighboring polarizable molecule in which dipole is induced causes a lowering of energy. An attractive interaction adds to the stability. In dipole-induced dipole interaction, okay, we're actually looking at dipole-induced dipole interaction. Stability is due to what? So you can see the answer there. London force, that's the final one. London force, induced dipole interaction. The only one that can explain liquefaction of gas like hydrogen, oxygen, chlorine, helium, and argon, which are all non-polar. So take note of that. This is the only one. The London force is the induced dipole. London gave an acceptable quantitative explanation for attractive forces existing between non-polar molecules. These forces are called dispersion force, since the oscillation producing the attractive force are also responsible for the dispersion of light by the molecule. So attractive force existing between one polar molecule is called what you can see that, and the only form of van der Waals interaction that best describes the liquefaction of gas, helium, is the only form of that. So that is the only form, induced dipole, as we have said. So London force in helium, on the average, the charge cloud allowed the helium atom to is symmetric. So when something is symmetric, it can have, maybe it can be circle, half part. If you take half, the up is the same like the other one. So electrons surrounding the nucleus of helium atom are in constant motion. Therefore, the helium atom can develop a momentary non-asymmetric electron distortion. That means once it is distorted, it's not the same. Dipole is induced. The consequence is temporary dipole arrangement of charge, otherwise known as instantaneous polarizability. The helium atom that has instantaneous polarity can then induce a dipole in neighboring helium atom. Just so that is how it can come up. So we have hydrogen bonding. Hydrogen bonding interaction involving hydrogen atom is located between a pair of other atoms having a high affinity for electrons, such bond is a weak bond. We can have hydrogen bonding in water, we have in ethanol, as you have known in your O-level chemistry. So it is a special type of dipole attraction. That is the hydrogen bond between hydrogen and electronegative element. And what are the electronegative elements? It can be something like oxygen. It can be hydrogen, oxygen. It can be hydrogen, nitrogen, like in ammonia. It can be hydrogen, carbon, like in hydrogen carbon or hydrogen hydroxide, like in ethanol, and the rest of them. So hydrogen bond strength range from 4 kilojoule to 50 kilojoule. So above that, hydrogen is not hydrogen bonded. The hydrogen bond have been destroyed. So its strength is between 4 and 50 kilojoules. So above that, it is destroyed. Because of the difference in electronegativity, hydrogen atom bears a large partial positive charge, and the nitrogen or oxygen or fluorine or chlorine atom will now have a large partial negative charge. The hydrogen atom in one molecule is electrostatically attracted to the other atom, and that is what we call hydrogen bonding. So we can see the hydrogen bonding in hydrogen fluoride. The hydrogen bonding is normally denoted by the dotted line. So like this molecule, because hydrogen is up, oxygen is up, there's a dotted line, that's hydrogen bond existing. So that is how it exists. Physical consequences of hydrogen bond, it can affect the boiling point. For instance, the boiling point of nitrosyl fluoride. Nitrosyl fluoride has a higher molecular weight. That means it is also affected by the hydrogen bond. nitrogen oxide, nitrosyl fluoride, and water have the same dipole moment, whereas it's not supposed to be so. But because of the hydrogen bond in water, they have the same hydrogen bond. So we also have a nitrosyl fluoride cannot form a hydrogen bond. Water can form hydrogen. So that's why they have the same dipole moment. So effect of molecular interaction on physical properties. It can affect polar molecules have higher melting and boiling point. So it makes them to have higher melting and boiling point. Among the noble gases, the boiling point increases with atomic number because the London force are more in large atoms due to higher polarizability. Among a series of similar non-polar molecules, such as hydrocarbon, boiling point increases with molecular size because of larger molecules, higher polarizability, and increased London force. So among the hybrid of group 5, 6, and 7, that includes something like ammonia, water, and hydrogen fluoride. They have higher boiling point because of strong hydrogen bond. So take note, between group 5, the hydride of group 5, 6, and 7, what makes them to have high boiling point is the strong hydrogen bonding bond. So you can see that explanation there. So that is what we see there. And there is striking contrast in the boiling point of the isomeric form, ethanol, and dimethyl ether. So they look like isomer, but the difference, what the hydrogen bonding between the molecule of ethanol contributes to a much higher boiling point. But the other hand, the molecules of dimethyl ether are held together only by weaker dipole-dipole interaction. So it doesn't have high boiling point. So London force also depend on the molecular geometry. For example, among the isomeric hydrocarbons, straight chain hydrocarbon have higher boiling point than the branch chain. So straight chain has higher boiling point than the branch chain. Ethanol have higher boiling point than its isomer, and the isomer is a dimethyl ether. So you can see that hydrogen bond can cause a higher boiling point. Which of the following will have higher boiling point? Pentanol, 1,2-dimethyl propanol, 1,2,3 trichloroethanol, none of the above. If pentanol is a straight chain molecule, as we have stated, straight chain molecule have higher boiling point than branch chain molecules. Have higher boiling point than branch chain molecule. So we summarize here that we have reviewed van der Waals force, we derived the cubic equation. We have actually talked about the van der Waals force and different forces of form of van der Waals force. We look at dipole-dipole interaction. We look at dipole-induced dipole interaction. We look at induced dipole interaction. So I will end this lecture here. The recording will be forwarded to the platform as usual. Thank you very much. If there's any question, you can sharply ask. You're welcome. I will take one day and treat several questions. I have so many questions I'll treat with you. So, but right, we will rush to finish the lecture. Towards the end of it, we'll treat questions so that we can help you know how to do that.
All right. So under physical consequences of hydrogen bonding,
yes,
there was this AMU as a unit. What does that mean?
Atomic mass unit.
Oh, okay, thank you.
Atomic mass unit. All right. Any other one? Thank you. See you next week.
Thank you, sir.
See you next week.